Okay, this is lesson 5 of module 6, increasing and decreasing functions. We'll be looking at graphs of functions and kind of analyzing the graph and different features of the graph to kind of relate it to the context of the story that generated the graph. So we're going to start with a couple of graphs of people running on different roads. It says, let's read the intro though. Not all real world situations can be modeled by a linear function. There are times when a nonlinear function is needed to describe the relationship between two quantities. So compare the two scenarios. Aleph is running at a constant rate on a flat paved road. The graph below represents the total distance he covers with respect to time. So this looks very much like a lot of graphs we've been working with. We've got time on the horizontal axis, and as the time increases, the total distance that he has run is also increasing. And because it's linear, it's increasing at the same rate the entire time. So we've got a constant rate situation. In the second graph, part B, Shannon is running on a flat, rocky trail that eventually rises up a steep mountain. The graph represents the total distance she covers with respect to time. So once again, this is clearly nonlinear because we can see the curve of this function. But again, we're graphing the same quantities, time and distance. And she's running. But notice nowhere does it say that she's running at a constant rate. So exercise 1 and 2 is going to walk you through looking at different intervals of time for both of these two runners on graph A and B. And you're going to analyze their rate on some different intervals of time, from 0 to 15 minutes, 15 to 30, 30 to 45, and 45 to 60, and talk about what's happening to their rate during those different times. So if you feel comfortable, you should go ahead and work on that now, either by yourself or with a partner or whoever it is that you're working with, or on your own. And come back and we'll check those together and then discuss the results. Okay, so we're asked between 0 and 15 minutes, how much, what is Aleph's rate? And so in 15 minutes, he covers a total of 2 miles. So where am I finding that? Okay, so he goes from 0 miles up to 2 miles in 15 minutes. Okay, so let's go ahead and record that. 2 miles in 15 minutes. Okay, because we're asked to describe what is happening as Aleph is running these different intervals of time. So between 15 and 30 minutes, let's go back and look at that. Between 15 minutes, which is right here, and 30 minutes, which is right here, his distance increased from 2 to 4, okay, which is what we would expect, right? Because he is traveling at a constant rate. So let's look at between 30, right here, and 45. We'll take 45 up to the graph. So we would expect another 2 miles. So there's 6 miles. And then between 45 and 60, another 2 miles, or 8 miles. So we can record that. So runs another 2 miles in this 15 minutes, the second 15 minutes. Okay. Okay, so in each of these intervals, he ran 2 miles in the 15-minute interval. And so over the course of 60 minutes, went 8 miles. So you might have said that his rate was 8 miles per hour, and that would have been correct. Okay, so his rate was 8 miles per hour on every one of those intervals, which is the definition of constant rate. All right, so now we're going to do the same thing for Shannon. So what is happening with Shannon? So let's look at that graph. Okay, so in the first 15 minutes, between 0 and 15, her distance went from 0 to, it looks like about 1 3/4, no, right here, to about 1.5 miles, just under 1.5. 1.5 miles in the first 15 minutes. Okay, so we want to say over here 1.5 miles in 15 minutes. And that's also the total run back to the graph. So in the second 15 minutes, she is going to go from here over to 30, go up to the graph. We can see that it's a little bit above 2. So so the increase, we went from, get my arrow here, we went from 1.5 up to 2.1, say. So it increased about 0.6 miles, 0.6 of a mile in 15 minutes. So what does that tell us about her rate? Or her rate. That her rate is decreasing, right? We went from 1.5 down to 0.6. So let's do it again. So from 30 minutes, we're going to start here at 2.1, and we're going to go to 45 minutes, which is right here. Read that on the y-axis. Looks like about 2.6. So she ran another 0.5 or half a mile in 15 minutes. So again, a little bit slower. And then let's look at from 45 minutes to 60 minutes. From 45 to 60, you can see here, each of these boxes again is half a mile. So it looks like about 0.4 because she's going to make it all the way, she's going to finish 3 miles in 60 minutes. So the next interval is about 0.4 of a mile. It's less than half a mile in 15 minutes. Okay, so as she's running, as time goes on, her speed is decreasing. And let's see where we see that on the graph, on her graph, okay? So it's a kind of steep right in the beginning, and then it gets less steep. It's still increasing, so it's not a negative slope. It's a positive slope, but it's not as steep here as it is down here. So why would that be? Well, let's go back to her story. She's running on a flat, rocky trail that eventually rises up a steep mountain. So she's not going to be able to go as fast as the other runner because it's a rocky trail. But she's going fast while it's flat. Here's where it's flat. And then here's where the mountain is steep. And so her speed is, she's slowing down. She's still moving forward, but slowing down. Okay, so it's a really good thing to do to look at different intervals of time and say, what is the slope between, say 30 minutes and 45 minutes. It's right there. What is the slope between 0 and 15? Well, it's right there. So it's steeper. Steeper in the beginning and slowing down as it progresses. Okay, so just to recap, this graph here is an increasing linear function, where Shannon's graph here is an increasing nonlinear function, because as time increases, the distance increases. So it's still an increasing function, but it is nonlinear. Okay, so let's look at the sketches of graphs in example 2. The rate of change of a function can provide useful information about the relationship between two quantities. A linear function has a constant rate of change, while a nonlinear function has a variable rate of change. So let's look at the different scenarios that can happen. So here's a linear function that is increasing at a constant rate, and here's a linear function that's decreasing at a constant rate. And then over here in the right-hand column, both of these are nonlinear. Now notice what's happening here. It looks different from Shannon's graph. So this is increasing. This is an increasing function. This is a decreasing function, because as x increases, so does y. And down here, as x increases, the y's are decreasing. But let's look at what's happening to the rate of change. Notice that this one is getting steeper and steeper and steeper. So this is increasing at a variable rate, and you can see that the rate is actually increasing as well. Whereas in Shannon's, her rate was decreasing, so it had more of a hump like this instead of curving up. And then this one below it is decreasing at a variable rate. So obviously not a constant rate, because this rate of change is getting steeper and steeper in both of these cases. Okay, so then if you look at tables, a table of values could tell you the same thing. On the left-hand side, this one, every time the x increases by 1, notice there's this is from 0 to 1, 1 to 2. The increases on the horizontal axis are all 1. These all go up by 3. Okay, so 7 to 10, 10 to 13, and so on. Whereas over here, we have the x's are all increasing by 1, and the y's, or the outputs, are increasing by a different amount each time. The first time it's 2, increases by 2, and then 2 again. So it looks like it's going to be linear, and then all of a sudden it increases by 4 and by 8. So the rate on these graphs are different. And remember, we did that in the past by just looking at the slope at 2 different points. So we could use these 2 points here. We would say that the slope, or the rate of change, is 2 minus 0 over 1 minus 0. And then if I choose these 2 points down here, I would have, which of course is equal to 2. And down here I would have 16 minus 8 over 4 minus 3. And that would give me 8 over 1, or just 8. So it's a variable rate of change. Probably easier to see with the graph already drawn than just with table of values. Okay, now we're going to try to sketch some graphs based on a description. So let's look at exercise 3. Different breeds of dogs have different growth rates. A large breed dog typically experiences a rapid growth rate from birth to 6 months. At that point, the growth rate begins to slow down until the dog reaches full growth around 2 years of age. Sketch a graph that represents the weight of a large breed dog from birth to 2 years. And so then we're going to be asked, is it linear or nonlinear? And then is the graph increasing or decreasing? So let's think this through. It would be really good if you would try to graph it on your own first and then come back. So why don't you pause and see what kind of graph you could sketch out. Okay, so there could be lots of good answers for this because we haven't been given any specific data about the weight of this dog. But what we do know is that up until age 6 months, that the dog grows very rapidly. So I'm going to draw a fairly steep graph for the first 6 months. So maybe going from, well, not quite 0 pounds, but just above, to up to about 30 pounds. Okay, then I'm going to have the rate's going to slow down. Well, begins to slow down until the dog reaches 2 years of age. So that's 24 months. So let's keep sketching our graph, and it's going to level off. And then if this graph continued, that dog could potentially stay at the same weight for the rest of his life. He would stop growing like that. So rapidly at first and then leveling off. So your graph should look something like this. It would not look like this because that would show slow rate in the beginning and then getting faster. So it wouldn't have that kind of a shape. It would be more of a hump type shape, like a little mountain here. Okay, so this is nonlinear, right? Nonlinear. And why is that? What in the problem tells us that this would be a nonlinear graph? Okay, it's nonlinear because growth rate is not constant. Growth rate slows down, I could say, something to that effect. Slows down. It's not constant. And the slope of this graph is measuring pounds per month that the dog grows. So we could see in the first 2 months, this dog grew 15 pounds. In the next 2 months, he grew maybe 10. And then in another 2 months, closer to 5. And so, so the rate is slowing down. And then when you get up here, this dog from here to here, in those 2 months, he only grew about, well, that was 5 right there. So down here, he was growing more like 10 pounds a month in 2 months. So anyway, the rate slows down, is not constant. Part C, is the function represented by the graph increasing or decreasing? This is an increasing function. Even though the growth rate is slowing, the dog isn't losing weight. So as the dog grows, the weight increases. Okay, so for the next several exercises, you're going to go through the same steps of reading a scenario, sketching a graph, deciding if it's linear or nonlinear, and then telling whether it's increasing or decreasing. So the best thing to do would be to pause and work on these on your own. If you want to come back after each one and check your work against the video, that would be good. Or you can do them all and then come back and check. It's up to you. All right, exercise 4. Nika took her laptop to school and drained the battery while typing a research paper. When she returned home, Nika connected her laptop to a power source and the battery recharged at a constant rate. Sketch a graph that represents the battery charge with respect to time. So again, your answer could be slightly different from mine, but because of this, we know this is going to be linear. So we could start down here at 0, 0 because she had no charge at time 0. And then we could say, well, I think it takes 3 hours to charge her battery. It didn't give us any numbers up there, no. So if I said she could charge it in 3 hours, I would draw a line something like that. The battery recharged at a constant rate. That means every hour it increased the same amount. Okay, so is the function represented by the graph linear or nonlinear? This is linear because, wow, that doesn't look like linear. It's linear because the battery charges at a constant rate. Okay, and then part B, is the function represented by the graph increasing or decreasing? Well, it's increasing because the battery is getting, as time goes on, the battery is getting more and more charged. All right, exercise 5 is sports. So the long jump is a track and field event where an athlete, I can't read this, attempts to leap as far as possible from a given point. Mike Powell of the U.S. set the long jump world record of 8.95 meters during the 1991 World Championship in Tokyo, Japan. And then we're asked, sketch a graph that represents the path of a high school athlete attempting the long jump. Well, so we know that they're not going to go 30 feet. So we could pick something, or 9 meters. We could pick a distance shorter. So say we think that athlete's going to jump 5 meters. That's what I'm going to guess. You could guess 6 or 7, but probably not anything over that. Sketch a graph that represents the path of a high school athlete attempting the long jump. So notice what we're graphing. We're graphing the length of the jump and the height of the jump. So the athlete starts his jump at 0 length and on the ground. Okay, so and then they have to get up a little bit, and then they're going to come back down. So at my total length, which I'm going to say is 5 meters, the athlete hits the ground again. Okay. Now, I don't know anything about long jumps, so I don't know how high off the ground they're going to go, but I'm going to guess maybe a meter or so off the ground. So they're going to jump up, their height increases, and then decreases over time, over the length of the jump. So in the middle of the jump, they reach their highest point, and then they start to come back down and land. Okay, so is the function represented by the graph linear or nonlinear? Explain. Well, this is nonlinear. Now we're not given data, so it's kind of hard to say. Somebody might think, well, it could be linear going up and linear coming down. But you have a sense that there's this gradual thing going on as this athlete jumps, his rate that he's rising tends to level off a little bit before he comes back down. So there's a sense that this is kind of a smooth curve, but we would need a little bit more information to know for sure. But nonlinear because the rate is not constant. The rate that he's rising with respect to the length of his jump is not constant. All right, so then we're asked, is the function represented by the graph increasing or decreasing? Well, it increases his height, and that's what we're talking about. The height increases up to the highest point and then begins to decrease. So it's both increasing and decreasing on different intervals of the function. So we could say, let me get a different color here. We could say, let's say this is his highest point right here. And it would probably be halfway through his jump, but just for the sake of argument. So on this interval, we'd say it's an increasing function. And then on this interval, the second half of the jump, it decreases. So it's both increasing and decreasing. This next example is a very different type of graph. So let's read what it's representing. Lamar and his sister are riding a Ferris wheel at a state fair. Using their watches, they find that it takes 8 seconds for the Ferris wheel to make a complete revolution. The graph below represents Lamar and his sister's distance above the ground with respect to time. Okay, so let's look at our the axis here. So we've got time in seconds and distance above ground in feet. So every 8 seconds, they are getting farther and farther and farther above the ground until they start to come down again to the lowest point, and then they'll start to go up. So if you've ever been on a Ferris wheel, you can see how that is. So down here I'm a certain amount above ground, and then I'm a little bit higher, and then every little bit of time I'm getting higher, and let's see, even higher. So it's going up. So this graph is measuring my total height above ground. I'm getting higher and higher. And then I hit my highest point and I start coming down. So here I'm decreasing, and I'm looking at distance above the ground. So I'm decreasing. Okay, getting closer, and here's closer, 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 closer. And that whole revolution took 8 seconds. Okay, so up and down and up. So I'm going around to my highest point and then back down again. So we're asked to use the graph from example 3 to answer the following questions. Is the function represented by the graph linear or nonlinear? Clearly this is nonlinear. So we know with a nonlinear graph that the rate of change is not a constant. Let's look at what other questions. We're also asked, is the function represented by the, well, we already did that one. Sorry, where is the function increasing? What does this mean within the context of the problem? So let's look back at the graph. Where is this an increasing function? Okay, so let's look here. So here, as time increases, as time goes on or increases, this is an increasing function here, but now it's decreasing. The height above ground is decreasing, then the height above ground increases, then it decreases. So how would we describe that? Okay, so we know that the function is increasing whenever they're going up on the Ferris wheel. So let's go back and see what intervals is that. So it would be from 0. This must be 4 seconds right here, because at 8 seconds they're back down again. This would be 8 right here. And then so the increase from 0 to 4, from 8, let's draw a line here wherever they've got. Wherever they hit. So on each of these intervals here, the function increases from here to here. So you can see here's increasing, increasing, and increasing. And let's use a different color to show decreasing. So here the function's decreasing on all of these intervals. So that's from here and here. So this function increases and decreases from 0 to 40 seconds as we go around here. So we can actually write those numbers. Where is the function increasing? Well, from 0 to 4 seconds, and then from 8 to 12, and then from 16 to 20, and then 24 to 28, and then 32 to 36, and let's go back and look. What else do we have? From 32 to 36. So as far as we're shown, that's the last one there. And then what does this mean in the context of the problem? That Lamar is rising. The car that he's in is rising up. Okay? And then where is the function decreasing? So that would be these intervals here from 4 to 8, from 12 to 16, from 20 to 24, from 28 to 32, and then from 36 to 40. Okay, so that's those intervals. And what does this mean in the context of the problem? Lamar is, how can we say this, dropping down. His car, the car that he's in, is coming down towards the ground. All right, we're going to be asked a couple more questions here. How high above the ground is the platform for passengers to get on the Ferris wheel? So let's look back at the graph for the clue to that. So let's clean this up. So the lowest, again, the height of, on the y-axis, we're saying that's the distance above ground. So the lowest that the Ferris wheel goes looks like is 5 feet right there. It always comes back down to 5 feet above the ground. So that must be where the platform is. The platform is at 5 feet. And to explain our reasoning, that is the lowest point on the graph. Okay, based on the graph, how many revolutions does the Ferris wheel complete during the 40-second time interval? And explain your reasoning. So we can go back and look at the graph again, and we can see that it makes 1, 2, 3, 4, 5 complete revolutions. And we could know that a couple different ways. We can see the rise and fall on the graph. And also we were told in the context of the problem that it takes 8 seconds. So in 40 seconds they would be able to make 5. Okay, so you should write more than that, explain your reasoning based on what I said. What is the diameter of the Ferris wheel? Explain your reasoning. Would this even be something we could know from this graph? So let's go back and look at the Ferris wheel and look at the graph. So we can see that the diameter of the Ferris wheel would be from here all the way down to where you get on. So from here up to here. So probably we could know the diameter. It would be the distance between the highest point, or rather the difference between the highest point that Lamar and his sister reach and that platform area, or the lowest point. So on the graph, that would be right here. The highest point they rise up to is 45, and they started at 5. So we could say that the diameter is probably approximately 40 feet for the reasons that we just stated. So you should put that into writing. It's the difference between the highest point and the lowest point that they reach. Okay, I hope you've enjoyed kind of analyzing these graphs. I think they're really interesting. You're going to see a lot more of this in your science and math classes in high school. When we look at a couple of these, if you look at a graph like this was the dog's growth rate. You could ask yourself, could this continue to increase indefinitely? And the obvious answer is no, because at some rate the dog is going to stop growing. We've observed that, and also eventually die, right? So this won't increase forever. Another one, let's look at this one. This is the battery charging. This one is going to only increase to this point, right? Once that battery reaches 100% charged, then it's going to just stay. In fact, we could draw another line like that. As long as she doesn't use her laptop, well, no. I mean, it'll stay charged until it starts to discharge, right? But it will stay 100% charged for a little while if she doesn't use it. So, but it won't continue to increase. So all of these functions, you're always going to be talking about an interval and what's happening on an interval. So just like this one, where we started, we analyzed each interval of time separately and saw what was happening to the distance in this case. So that's what you'll be doing with graphs in the future too. So this is really interesting and kind of fun. It's a bit of a puzzle. Sorry, didn't mean to make you dizzy there. All right, so the graph of a function can be used to help describe the relationship between two quantities, whether it's time that a laptop's plugged in and the percent of charge, or time running and distance traveled. What else do we do? Length of a jump compared to the height of a long jump. So there's always two quantities, and the graph will tell a story about how those two quantities are related. Okay, so a linear function has a constant rate of change. A nonlinear function does not have a constant rate of change. So these graphs can be increasing, can be decreasing, and some functions may increase and decrease over different intervals. All right, so you're going to be asked to do the same thing in these scenarios. Remember that if you're asked to sketch a graph, there can be a range of answers that make sense. So just be prepared to defend your answer. All right, good luck with that.